Hi, everyone. Great. Well, today we're going to continue talking about ferromagnetism, which we introduced last time. And I'd like to talk about the mean field model and see how we can explain some of the phenomena that we saw last time, and then go on to talk about some applications of ferromagnetism, which I think are really exciting. Okay? So here, let's look at an outline and see where we are in our discussion of magnetic phenomena. Very good. Well, we've been talking about magnetism, of course. We've covered some of the basics. We talked about paramagnetism, and in particular Curie susceptibility and Pauli susceptibility. And then last time we talked about ferromagnetism. We introduced the exchange interaction. We showed that the interaction that makes spins want to align in a ferromagnet is not fundamentally a magnetic interaction between the spins, even though the spins do have an associated magnetic moment. It's actually electrostatic, and it's governed by the Pauli exclusion principle. Okay? And it's very, very strong, many thousands of times stronger than the magnetic interaction between two spins would be. We introduced a model of the interaction of the it lets us calculate the exchange energy for a solid, the Ising model and the mean field model. And we talked about the Ising model last time and looked at a simulation. And our simulations showed some really interesting phenomena. First of all, it showed that in this model ferromagnetic material, the behavior depended a lot on temperature. At high temperatures, the material behaved like a paramagnet with a linear susceptibility at low fields. But at low temperatures, the material behaved like a ferromagnet with spontaneous magnetization that organized into domains, as we expect in a ferromagnet. So there was a phase transition temperature at which the material goes from a ferromagnetic phase to a paramagnetic phase. That's really interesting. And that's a phenomena that's observed in real ferromagnets. The phase transition temperature is called the Curie temperature, and every ferromagnet has a Curie temperature above which it acts like a paramagnet. Okay? The other interesting phenomena we saw was remanence and hysteresis. That is, we could magnetize a ferromagnet with a magnetic field, but then when we remove the magnetic field, it's possible to have a remanent magnetization. The material stays magnetized even in the absence of an external magnetic field. And it can exhibit hysteresis. The magnetization in one direction can even persist when we add a field pointing in the opposite direction, as long as this field doesn't get too strong. Okay? So those are things we'd like to understand further. And today, we'll see what we can get by looking at what's called the mean field model. Okay? It's kind of the opposite of the Ising model. The Ising model only looked at nearest neighbor interactions. This one is going to kind of average over the whole material. Well, let's have a look. And once we've done that, then we'll be ready to talk about some applications. All right, hang on. All right, last time we introduced the exchange interaction, and we figured out how to calculate the total exchange energy for a particular ion. So we can calculate the exchange energy between one ion and another. Oh, excuse me. And the total energy for a particular ion. Oh, I'm sorry, which I want to write this way. And we could write this in the following way. 1 second. There we go. All right. So that's what we had found last time. In order to find the total magnetic energy, or the total exchange energy for a particular ion, we just have to do this sum. We have to take the dot product of that ion with a vector formed by summing up over all the other ions in the crystal, the exchange energy times the times the spin angular momentum of the other ion. And we said, well, that's a very complicated thing to do. Okay. We looked at the Ising model where we restricted ourselves to nearest neighbor interactions. And now we're going to look at something called the mean field model. To start the mean field model, we're just going to rewrite this equation in the following way. Okay. We're going to say that the total energy for a particular ion, we're going to write as, well, we could write, since the magnetic moment of ion I is proportional to its spin, we could write this as minus m sub I, magnetic moment of ion I, times some other terms. And we'll call those other terms an effective, we'll call those other terms, B sub E, where B sub E here is, it's really just the name for all these terms. It looks like a magnetic field here, and that's intentional because it behaves like a magnetic field, but it's not a magnetic field. It's what's called the exchange field. Okay? And we can easily see that the formula for the exchange field then, it's just, well, it's all these other terms. We also have to divide, and one other thing. So the exchange field is clearly 2 times the sum over all the other ions of J, I, J, S sub J. And then we have to divide by Bohr magneton because we're talking about magnetic moments and magnetic fields now and not angular momenta. Okay? So the important thing to recognize here is this is a useful way to think about things. But when we do that, we have to be careful. The exchange field here is not a magnetic field. Instead, it's just a way of thinking about the exchange interaction, which makes the spins want to line up, just as a magnetic field would. But while it's not a magnetic field, we can think of it as being like a magnetic field and also thinking of it having a strength that we can describe in Tesla. And when we do that, we find that this is very large. So in units of Tesla, it might have a strength of 10,000 Tesla, okay? Not a magnetic field, but equivalent to a very, very strong magnetic field, okay? All right. Well, so far we've just introduced a new idea of the exchange field. And then here's an important point. The value of the exchange field fluctuates as we move through the crystal. Because of variations in local magnetic moments. And that makes this a very complicated thing. So in mean field theory, we use the mean field approximation, which is we replace this exchange field with the average exchange field. Okay? That's the mean field approximation. And we can then use the mean field approximation to try to understand some of the phenomena we observe in ferromagnets. Okay?